welcome to this module, and in this module what we will look at? We will look at how to deposit a piezoresistive material on the interdigitated electrode, and those interdigitated electrode, as you remember from our last module, were fabricated on a silicon dioxide material, and that silicon dioxide acts as an insulator between a micro heater and interdigitated electrode. So, just to help you out, what we have studied? We have studied how to fabricate a heater on oxidized silicon substrate, how to deposit an insulating layer, open the contacts of the heater, then deposit metal which is for the interdigitated electrodes, and then we have patterned IDEs. Now, we will see how can you deposit piezoresistive material over IDEs using two techniques. One is the standard lithography technique, and second one which I will teach you today, which is called lift off. Okay. So, if you see the slide, as you know, our goal is to understand how can we fabricate this particular chip. When you want to fabricate this chip, like I said, this chip is indicated with a micro heater. This chip is indicated with interdigitated electrodes. On interdigitated electrodes there are piezoresistive materials, and on that we have another insulator. On that there is a gold pad, which is over that there are SU 8 pillars which are we made it conductive. On the back side of chip there is a diaphragm, and I will tell you what is the role of the diaphragm when we understand the fabrication of the complete chip. Okay. So, this we have seen, this we saw in the last module, correct. Now, we will continue from this process onwards to deposit a piezoresistive material in this region 1, 2, 3 and 4. Okay. So, this is just a magnified view. This is what I want to do today. I want to teach you fabrication of piezoresistive sensors on the interdigitated electrodes. Alright. So, let us see the process flow. So, let us see how can we fabricate the piezoresistive sensors over the interdigitated electrode. For that, what we will do? We will first take the oxidized silicon wafer, and we have seen that our oxidized silicon wafer is integrated with micro heater, right, and then we have opened the contact, correct. This is our contact region which is opened, you can see right over here, and this is my silicon dioxide which is grown using PECVD. We all know, right, silicon dioxide 1, silicon dioxide 2, silicon dioxide 3, silicon, and then we have our nichrome. This is a heater material, right. Over that, what we have seen yesterday or in the last lecture, that we have a metal, right. So, let me represent the metal by this design, and this is our interdigitated electrodes, interdigitated electrodes. Now, over this I want to deposit a piezoresistive material, right. So, there are two ways. Now, this interdigitated electrodes we have used chrome gold, right, but you can also use any other metal, right, any other metal. All right. The silicon dioxide, let this one and this one is grown using thermal oxidation, while this silicon dioxide is deposited using PECVD. So, let me first explain you why we have not grown silicon dioxide using thermal oxidation like this to thermal like this oxidized or silicon dioxide layer that we used thermal oxidation. Why we have not used thermal oxidation for this silicon dioxide? Why we have used PECVD? Okay. Let me first explain you that, and then we will move to the piezoresistive material. You see, PECVD, we can vary the temperature from 100 degree centigrade to 400 degree centigrade for the chemical vapor deposition. Thermal oxidation, the temperature is 1100 degree centigrade. Again you can vary from 1000 to 1200, generally it is 1100 degree centigrade. Okay. Now, you have nichrome. So, I will just draw quickly a heater on oxidized silicon wafer, right. See, please understand the term, this is a silicon wafer. When you grow silicon dioxide on silicon wafer, it becomes oxidized silicon wafer, oxidized silicon wafer, all right. So, oxidized silicon wafer, we are fabricating a micro heater, right. This is our structure. On this, what we said, I want to deposit or I want to grow my silicon dioxide, or I want to deposit my silicon dioxide on the heater, right. So, that I can further process my wafer to fabricate interdigital electrodes and other materials. Now, if I use thermal oxidation to grow this silicon dioxide, the temperature that is used is 1100 degree centigrade, while the material can be nichrome or it can be nickel for my micro heater or for my heater, right. So, this material which is nichrome or nickel should withstand 1100 degree centigrade, right. If it cannot withstand this high temperature, then what will happen? It will melt, right, it will melt, and that is why we want to grow silicon dioxide or we want to deposit silicon dioxide at a lower temperature. You got it? Because if I use thermal oxidation for growing this silicon dioxide, then my temperature is around 1100 degree centigrade, and that temperature the material below it, that is the material below silicon dioxide, which is my nichrome or nickel for my micro heater, should withstand. Now, if it cannot withstand, then I will not get the heater, it will melt, and that will create a problem. So, to avoid that, I will deposit silicon dioxide using a technique called plasma enhanced chemical vapor deposition, right. It stands for PECVD, right, and the advantage is that we can deposit at a lower temperature. You got it? That is why I said that for insulating layer over heater we will go for PECVD, right. So, that is the reason of using PECVD instead of the thermal oxidation. Okay guys, easy, very easy, right. Once you understand fabrication, it becomes very easy to design the chip, and once you design the chip, then we will go for this system design, alright. Now, this is the material. Over that what we have to do? So, I will again draw the schematic where we can see what? Silicon dioxide, silicon, heater, insulator, interdigitated electrodes, right. Interdigital electrodes, this is my silicon dioxide. On this I will deposit, sorry, on this I will deposit a piezoresistive material, piezoresistive material. Now, there are piezoresistive materials which can be deposited using PVD. PVD stands for physical vapor deposition, physical vapor deposition. Three types: thermal evaporation, electron beam evaporation, and sputtering. All right, physical vapor deposition, thermal evaporation, E-beam evaporation, and sputtering. So, using E-beam evaporation or sputtering, we will deposit piezoresistive material. Okay. Now, there is an alternative material which is a conducting polymer. Now, this can be zinc oxide, right, or any other piezoresistive material, but if I want to use conducting polymer, generally polymers are non conducting, but if I want to use conducting polymer, I can use P dot PSS, and for using P dot PSS I have to spin coat it, spin coat on interdigital electrodes. This is also piezoresistive material. Okay. So, point is that we will deposit or we will spin coat piezoresistive material, right, using either PVD or using spin coating, right. Once you do that, what you have to do? You have to perform lithography, and all of you know how to perform lithography. We will spin coat positive photoresist, right. Let me put checks for positive photoresist. What after that? What is the step after positive photoresist? I will soft bake the wafer, at 90 degree centigrade for 1 minute. All right. And after soft bake, next step is to load the mask, and we only want the material which is a piezoresistive material to be on the interdigital electrodes and not on the contact region, right. Is it correct mask? No. So, I will also show it to you two different ways. If I use bright field mask, like this one, right. This is my bright field mask, and if I expose the wafer with UV, what will happen? The unexposed region will be stronger. But if I do not have bright field mask and I have a dark field mask, and I have a dark field mask, right. In that case, my dark field mask will look like this. Right. So, in this case, if I use positive photoresist, then the region which is unexposed will be stronger, which we do not want. We want our piezoresistive material to be on this area, right, only on this area, we do not want on the contact. So, if I use dark field mask with positive photoresist, my problem will not solve. So, what I will do, I will, if I have, sorry, let me just select the red color. Okay. If I have dark field mask, then I will change my positive photoresist, instead of positive photoresist I will spin coat negative photoresist. You got it? Because if in negative photoresist the unexposed region will be weaker and the exposed region, which is this region, will be stronger. So, finally, what we will have, we can save the piezoresistive material over this particular region, which is our region of interest, and there will be nothing over the contact. You got it? So, very simple. If I have dark field mask, I will go for negative photoresist in this case, but if I have a bright field mask, then I will go for a positive photoresist. So, you have to select the recipe according to the design of your mask and the availability of a photoresist, right. So, here I will use positive photoresist. This is my bright field mask. Easy. After exposing, what will happen? We have to develop the photoresist, PR development, right. So, if I dip the wafer in photoresist, which is photoresist developer, then what will I have? I will have my oxidized silicon wafer, on that there is a micro heater, on that there is a insulating material, which is my silicon dioxide, on that I have interdigitated electrodes, right. On there is a piezoresistive material, this is silicon dioxide using PCVD, silicon dioxide using thermal oxidation, silicon dioxide using thermal oxidation, silicon wafer, nichrome, chrome gold, right, and piezoresistive material. Over that I will have my photoresist only in this region, Okay. Why? Because I have used a bright field mask with positive photoresist and the unexposed region will be stronger, and that is why I can see that the unexposed region is stronger. The next step is we will go for a hard bake. Hard bake is done at 120 degree centigrade 1 minute on hot plate. After this, the next step would be to etch piezoresistive material. So, we have to dip this wafer in a piezoresistive material etchant, right, wet etching. If I do that, what will happen? The material which is protected by the piezoresistive material, which is protected by the photoresist, will not get etched, but the piezoresistive material which is not protected by photoresist will get etched. So, I will have piezoresistive material in this area. All right, you got it, because there is no photoresist that can protect the piezoresistive material in this region and this region. So, once I deposit the wafer or once I dip the wafer in a piezoresistive etchant, I will etch my piezoresistive material which is not protected by photoresist. Next step for this would be that I will dip this wafer in acetone. If I dip the wafer in acetone, what will happen? We will strip off, we will strip the photoresist. If I dip the wafer in acetone, we will strip the photoresist. If I strip the photoresist, then what will I have? I will have a piezoresistive material over interdigitated electrodes, right. I will have a piezoresistive, like say piezoresistive material over interdigitated electrodes over SiO2 over nichrome heater, and then this will look like this one. You got it? Easy. So, what is our next step? Our next step is to have a gold pad, right, which is in the center, okay, this one gold pad, and on that gold pad we require SU8 pillars. On that gold pad we require SU8 pillars. So, can I deposit the gold directly on piezoresistive material? This is piezoresistive material, right. These 4 black squares in center or gray squares in the center are piezoresistive materials. But can I deposit a gold which is a metal on piezoresistive material? It will get short, right. So, what we have to do after this, we have to grow a silicon dioxide layer, right, open the contacts in all the area except in this area, right, and then we will deposit metal, we will pattern it to form the gold pad. So, till now let us see in this particular module what we have learned. We have learned how to deposit a piezoresistive material on interdigitated electrode. But like I said, I want to teach you in this module itself what will happen if I want to use lift off. So, what exactly lift off means and why we have to use lift off, right. So, let us understand, if you go back to the slide, what you see here is that we have done a standard lithography technique where we have piezoresistive material. So, if I just continue from this section, it will be easier for you to understand why we will go for lift off. Okay. So, the point is that you know that we had a piezoresistive material all over the interdigitated electrodes, and then we are protecting the piezoresistive material in this area, right. This much we all know. This is positive photoresist, this is piezoresistive material, okay. This is of course chrome gold and remaining structure you know. So, now if I dip this wafer in piezoresistive material etchant, in piezoresistive etchant, what will happen? It will etch the piezoresistive material, right. It will etch the piezoresistive material. Suppose the etchant of the piezoresistive material also affects the chrome and gold, then what will happen? Once the piezoresistive material is etched from the area which is not protected by photoresist, it will start etching chrome gold. It will start etching chrome gold. Why? Because the piezoresistive material that we have used, the etchant, the chemicals that are used to etch piezoresistive material will start affecting chrome gold, because the material or the chemicals are such that it can also etch chrome gold. In this case, what will happen? The chrome gold here and here, right, will be etched. If that is the case, we will lose the contact to the interdigitated electrodes, correct. We will lose the contact to the interdigitated electrodes. Then what is the purpose of fabricating interdigitated electrodes? No purpose, it is gone. There is no point of continuing with the fabrication, right. So, if this case arises when you are fabricating a device, what you have to do? You have to think of an alternative technique to pattern piezoresistive material, which is called lift off. So, let me show you. Interesting, if you see the slide, I will show you how to do lift off. Okay, very interesting technique, very easy focus on the schematic that I am drawing, right. So, I always write down, even you know that what are the patterns here, what I am showing in the design is always a good practice to write down as many times as you can, so that you remember. Okay. This is using thermal oxidation. Over that what we have? We have a heater. Over that what we have? We have a silicon dioxide grown using PECVD. Over that what we have? We have interdigitated electrodes, correct. Now, over this we want to pattern the piezoresistive material. So, for patterning the piezoresistive material, what we will do? We will use a technique called lift off. What is this technique? Lift off. So, we will first, instead of depositing piezoresistive material, we will spin coat positive photoresist. Alright, we will spin coat positive photoresist. Then we will use a dark film mask, Of course, after positive photoresist spin coating, what is the next step? Next step is of course the soft bake, right, is soft bake. So, spin coating, soft bake at 90 degree 1 minute hot plate, we will load the dark fill mask and I have positive photoresist. So, if I expose dark fill mask with UV, what will happen? The unexposed region will be stronger and the exposed region would be weaker. So, what will I have? I will have an oxidized silicon wafer with heater, insulating material, interdigital electrodes, right, and photoresist. So, let me draw photoresist like X. So, photoresist in this region, right. So, if I use positive photoresist, if I expose the wafer with UV and if I develop the wafer what will I have? I will have photoresist. In this region there is nothing, you can see there is no photoresist, right, there is no photoresist, but here there is photoresist and we know what is this one? Interdigital electrodes, right, interdigitated electrodes made from gold, or you can say chrome gold, nichrome, silicon dioxide, silicon dioxide, right. Now, I will go for hard bake, 120 1 minute hot plate. After hard bake, next step is I will deposit a piezoresistive material. Piezoresistive material will be deposited like this, right. So, let me just draw the piezoresistive material with a different color. So, you understand this is a piezoresistive material, right. What I have done on the positive photoresist, which after the hard bake I have deposited a piezoresistive material right over the photoresist. The next step is, after this I will dip the wafer in acetone, I will dip the wafer in acetone. If you dip the wafer in acetone, what will happen? The positive photoresist will be stripped off, it strips off, right. So, if the positive photoresist strips off, it will lift off the material over it, So, what does that mean? If I dip this wafer with a piezoresistive material deposited on positive photoresist, and if I dip this wafer in acetone, then what will I have is this structure. You got it? Why? Because the positive photoresist will lift off the material when you strip it in acetone. You got it? So, why and now you have to do a lift off? Because then this way you are not using an etchant for the piezoresistive material, and that way if my etchant is, or the piezoresistive etchant or the material etchant is affecting chrome gold which is right below it, now in this case it will not be a problem, because we are dipping the wafer in acetone which will strip off the photoresist, and the piezoresistive material will stick to the interdigitated electrodes, right. So, this is the last slide for this particular module, and what we have seen? We have seen how can we deposit piezoresistive material, right, on interdigitated electrodes which are on silicon dioxide, which are on micro heater, right. So, if you go from the bottom, oxidized silicon substrate, micro heater, silicon dioxide, interdigitated electrodes, piezoresistive material. Piezoresistive material either using the standard lithography or using lift off technique, right. In the next slide, in the next module, in fact, what we will see? We will see how can we deposit a gold pad on a piezoresistive material. And like I said, that if you want to deposit a gold on piezoresistive material, you again have to form an insulating layer, right. So, till then just go through this particular module, and I will see you in next module. Take care, bye.